Ohore handia da niretzako, atom by atom biltzarraren azken izlariaren aurkezpena egitea. It's a pleasure for me to introduce the last speaker of this conference, Albert Fert. He's a Nobel Prize in Physics, fizikako Nobel sariduna. Frantziako Karkason hirian jaioa, matematika eta fizika ikasketak egin zituen Parisen, eta 1970 garren urtean doktoregoa lortu zuen, material ferromagnetiko batean elektroiek duten higikortasunari buruzko lanari esker. Garai hartan, nanoeskalako geruza meheak egiterik ez zegoen 1970 garren urtean, baina 15 urte geroago, lanari, ideiari, gaiari ekin zitzaion, berriro eta magnetoerresistentzia erraldoia izenaz ezagutzen den fenomeno garrantzitsua aurkituko zuen. Doktoratu ondoren, Erresuma Batuko Leedseko unibertsitatera abiatu zen, ikerketa lanetan jarraitzeko, eta handik Parisera itzuli zen egoera solidoaren fizikako laborategi batera. 1976 garren urtetik ona, bertako irakasle katedraduna izan da. 1988 garren urtean, lehen aurreratu dudan bezala, magnetoerresistentzia erraldoia aurkitu zuen burdina eta kromozko multigeruzetan. Aurkikuntza honetan oinarritzen da neurri handi batean gure gailu elektronikoen diska gogorren funtzionamendua eta nanoteknologiaren aplikazio aitzindarietakozat hartu ohi da. Teknologia hori gainera elektronikaren aro berria, spintronikoa, izan litekeenaren lehen urratsa dugu. Aurkikuntza garrantzitsu horregatik, fizikako Nobel saria lortu zuen 2007 garren urtean, orain dela 2 urte, Peter Gruenberg fizikari alemanarekin batera. In his lecture, he'll give us an introduction about the fundamentals of spin-dependent conduction, the concept of giant magnetoresistance, the applications of this novel phenomenon, and what could be a completely new type of electronics, the so-called Spintronics. Estoy seguro de que el profesor Fert nos ayudará a entender de primera mano la realidad de este apasionante campo de investigación en la nanoescala. Le paso la palabra al profesor Fert.
Okay, so I thank Professor Pitarch for the introduction. I could have understood in Castellano, in Catalan, in Francés también. En Basque is muy difficult. But I will try next time. Okay, so I thank also the organizer for the invitation. So my talk today will be on Spintronics. Spintronics is well known mainly only for the giant magnetoresistance and the application of the giant magnetoresistance of the GMR. We use GMR to read the hard disk of our computer every day or to listen to music from the iPod. But in my feeling, okay, the discovery of the giant magnetoresistance was only a stage in a much longer development. There was something before, the basic physics of the influence of the spin on the electrical conduction in magnetic material, and this physics led to the discovery. And after, there was an intense research boosted by the nanotechnology, which nanotechnology was also important, and this intense research led to many other effects, to reveal many other effects also related to the influence of the spin on the electrical conduction. And now this field called Spintronics is expanding in many directions. And there are already many other applications, and there will be many applications of this field. So this first projection gathers some of the most active field of research today in what I call classical spintronics. There is still an interesting advance on the tunneling magnetoresistance and more generally on the spin filtering effect, the basis of spintronics. Spin transfer is a very active field of research. What is a spin transfer? In a spin transfer experiment, you can manipulate the magnetization of a ferromagnetic body, of a magnet, without applying a magnetic field, only by a sort of transfusion of spin angular momentum brought by an electrical current, a sort of transport of magnetization at distance. And this transfusion of spin can be used either to switch the magnet, to switch the magnetization, and this will be used relatively soon to hide memories, to switch magnetic memories, MRAMs. And in other conditions, this can be used also to generate oscillation of the magnetization and generation of microwave, emission of microwave. And this will have also relatively soon application in telecommunications. And there are other very active fields, spintronics with semiconductor, where, of course, it is very attractive to combine the potential of conventional electronics with semiconductor is the potential of spintronics. Spintronics with carbon-based material, graphene, nanotubes, is very attractive, really very promising. And there is also single electron electronics, which is one on the way to quantum computing. So I will describe some of these recent developments, but for those who are not familiar of this field, I will begin by a general introduction on the basic physics, that is the influence of the spin on the conduction in ferromagnets. And so it can be understood easily. If you look at the energy bands in a ferromagnetic metal like iron, cobalt, there is a splitting between what is called the majority spin band and the minority spin band, spin up and spin down. This is the origin of the ferromagnetic because the filling is different. The filling up to the Fermi level is different for these two spin directions. And if one considers the electrical conduction, which is controlled by the wave function of the electron at the Fermi level, one sees that the wave function are completely different. The electron states are different at the Fermi level for the two spin directions, and very generally there is a spin-dependent conduction. And in first approximation, it can be described by a conduction by two channels in parallel, spin up, spin down, and the contrast between the conductivity of the two channels can be very large, especially when one dopes the material with impurity, also introducing strongly spin-dependent scattering cross-sections. For example, you can see the resistivity for of the two channels up and down introduced by and used by 1% of several types of impurity in nickel. You can see, for example, if you dope nickel with cobalt, the resistivity of the spin down channel is 20 times larger than the resistivity of spin up, and this is the contrary, for example, for chromium or vanadium. So these results are not new. They are from my PhD thesis in 70, a long time ago. And at this time, they could be understood by using the electronic structure model, for example, developed by Friedel. For example, if one want to understand these results, one consider the resistivity is controlled by the relative position of the impurity level and energy band for each spin direction. And this relative position is different for spin up and spin down, and explain more or less this curve. Also, at this time, we had some practically some concept very close to the concept of the giant magnetoresistance in experiments in ternary alloys. Suppose that you introduce doped nickel with two types of impurity, E and B, and first suppose that they have opposite spin asymmetry. That is, the impurity E will introduce a strong obstacle in the spin down and will leave more or less free the spin-up channel. And the contrary, the opposite for B. If you put at the same time in the same alloy E and B, of course, there will be strong scattering. The electron will be slowed down in both channels, and the resistivity will be strongly enhanced. Experimental confirmation below for nickel with cobalt and rhodium can see in Steve for a total concentration of 1% as a function of the proportion. Instead of a linear increase in the middle, you have a relatively strong increase of the resistivity of the alloy. On the contrary, if the resistivity, the impurity is chosen with the same spin asymmetry, of course, they will block more one of the channel, but this channel will remain free, and this enhancement will not occur. Experimental example with gold and cobalt. And what is the concept of GMR? Is simply replacing the two impurity E and B by two layers, E and B. The situation of the left will correspond to opposite magnetization of the layer. That is, the electron in one channel will be stopped by this layer, and in the other channel by the other layer. And on the contrary, the situation with parallel magnetization will correspond to the situation with a small resistivity. The difference is that it will be possible to switch rapidly simply by applying a field from the left to the right instead of melting another alloy. But if we know the transport equation, you know that the electron will be able to fill the relative orientation of the two layers if the distance between the two layers is smaller than the mean free path of the electron, which in this metallic layer is of the order of few nanometers. So at this time, it was not possible to prepare multi-layers with simply a thickness of only a few nanometers. The nanotechnology were not accessible. And so this sort of concept was requiring an advance, the onset of the nanotechnology. So, but in the 80s, with the microelectronic, it became possible to prepare this sort of very thin multilayer with technology like the molecular beam epitaxy. And so we had a collaboration with the company of microelectronic, Thomson, to prepare this sort of multilayers. You see the balls represent atoms, 3 atomic layers of iron, 3 atomic layers of chromium, etc. Why chromium and iron? Because Peter Gunberg, my Nobel Laureate, found in '86 that for a very thin layer of chromium, there was an exchange interaction between the magnetic interaction, if you want, between the two adjacent ion layers, so that the magnetization are in opposite direction. So this was the ideal system to be able to proceed by applying a field from this entire parallel orientation of the magnetization to a parallel orientation. And this led to the discovery of the GMR in Orsay and by Peter Gunberg in Jülich. So this is a typical, the initial GMR curve we published in '88. So as a function of the field, as the field destabilize the anti-parallel configuration and align the magnetization of all the ion layer, and the magnetoresistance is a corresponding drop, 80% of the resistance of the multi-layer. And the same results in Germany. So the mechanism is exactly what I can repeat what I say for the ternary alloys. When all the magnetization are parallel, this one of the spin direction will be can go through easily through all the magnetic layer, and due to this shorting of the current by the channel, the resistivity is low. On the contrary, in the anti-parallel configuration, the electron are slowed down every second layer in both channels, and the resistivity is high. In fact, even if the current is along the layer, the current is there is a random also velocity of the electron, so that finally the mean orientation is oblique. And of course, the condition is that the thickness of the layer should be smaller than the mean free path of the order nanometer. You can see that indeed the best value, the largest value of the GMR obtained for very small thicknesses, for example, less than 1 nanometer for this curve. Okay, so of course this picture is too simple. Then for a realistic interpretation, one is necessary also to take into account the reflection of the electron at the interface, to take into account the roughness of the interface. But I don't want to discuss all these details of the interpretation of the GMR. I say simply a few words on the application. I was supposing having an image of application. The most important economical application was the application to the hard disk. On the hard disk, the detection, you have to detect the small field generated by the very small magnetic bits. And so now you can detect in your hard disk, you can detect this small magnetic field with a multi-layer. This is a GMR sensor. And so with the sensitivity of the GMR, it became possible to detect. So the detection is that when the multi-layers see one of these small fields, this field align all the magnetization of all the layer, and the resistivity drop, and you can detect the increase of electrical currents. And so the sensitivity of the GMR allow to detect smaller fields, smaller bits, and to increase the density, the number of bits you can put in the same disk. For example, this density has been increased by almost, I don't know, the last number was 600 from the generation before. And also because it became possible to put a lot of information on very small area on disk of the size of a coin, it has been possible to extend the technology of the hard disk not only for the computer but also for consumer electronic, iPods, telephones, some cameras. And so this also enlarged considerably the market of the hard disk and the importance, the economical importance of the GMR. So I proceed to another important stage of the development of spintronics, tunneling magnetoresistance, spin-dependent tunneling TMR, again 2 magnetic layers, but now separated by a very thin insulating layer. The effect, the TMR, tunneling, is more or less like the GMR. Now the transport is by tunneling and by the quantum mechanical effect called tunneling. And the effect is the same. The resistance of this tunnel junction will be different for the parallel and anti-parallel configurations. The advantage is that with this vertical geometry of the current, it's possible to reduce the lateral side by e-beam lithography, for example, a new technique, and to have very small cells, very small device. This effect, the general magnetoresistance, was observed but not very reproducibly in 1975 by Julier. But then the effect is this junction are very difficult to fabricate. But now Mudera and Miyazaki in 1995 succeed in fabricating a tunnel junction with an aluminum barrier and to obtain very reproducible results. And now this first generation of tunnel junction is at the base of several applications. They are used in some read-S of hard disk and also in MRAMs put onto the market by Motorola 3 years ago or 4 years ago. In fact, what is a MRAM? You know that in your computer you have a massive memory in the hard disk, but the disadvantage of the hard disk is that it takes some time to keep the information, to find the information. 1 millisecond for 1 bit. This is much too slow for the computer of today. And so when you switch on your computer, you take a part of the memory of the disk to fill RAM, what is called RAM, semiconductor memory, that have a very short access time, 1 or a few nanoseconds, but with the disadvantage of being volatile. That is, when without power, when we switch off the computer, the memory dies. You have to save your work before switching off the computer, and also for the most the less expensive of the memory, the DRAM, you have to refresh the memory every millisecond. And so the objective of the MRAM is to have the similar access time than the RAM, but with a permanent memory, because this memory, if this can be a memory cell, 0 and 1, but with a permanent memory. And so this is the objective, having the density and the speed of the RAM, plus the non-volatility and certainly low energy consumption. The first generation has only small impact on the technology of the computer, some impact, but small, but much more is expected from the next generation of STT-RAM. The difference with the STT-RAM in development in many companies in the world is that they will use the recent advance on the tunnel junction, much larger TMR ratio, and also the writing by spin transfer, simply by transport of magnetization by electrical currents. And so I will come back on the spin transfer, and I will say a few words on the MGO tunnel junctions. First, the advance came from the for the transition with single crystal multilayer. So an advance in technology that allow people to prepare this type of single crystal tunnel junction. For example, you can see the atomic lines, atomic planes in MGO, in iron on both sides. And these magnetic tunnel junctions have very large magnetoresistance ratio. 500% means that the resistivity increase from 1 to 6 when one goes from parallel to anti-parallel configuration. And I want to say a few words on the physics, why the TMR is so large, because the physics is really interesting and also illustrate clearly what can be under the word spin polarization. We have seen that for metal, spin polarization is not really related to the property of the pure metal, but can be changed by introducing some impurity that scatter spin up or spin down. And you will see that also MGO is very important in the performance of this tunnel junction. In fact, this can be described this way. In a single crystal insulating material, the transport is by evanescent waves, and decreasing exponentially. But in a crystal, these waves are of different symmetry, like in any crystals. So in this case, delta 1, delta 5, delta 2. And it occurs that in MGO, delta 1 is a much better channel. The wave of symmetry delta 1 decreases only slowly as a function of the distance, and so this is the good channel for the transport of electrons from one side to the other. Also in the metal, there are waves of symmetry delta 1, delta 5, delta 2, and if the interface is of high quality, again, the nanotechnologies, the delta 1 is connected to the evanescent wave of symmetry delta 1. And so the situation, and it occurs, the key point is that the symmetry delta 1 is present in the majority spin band, subband of cobalt, but not in the minority spin band of cobalt. So there is no problem when the configuration of the two layers is parallel, then this an electron majority spin delta 1 symmetry electron can go through the channel and be accommodated in a state of symmetry delta 1 of the majority spin subband. But when the magnetization, the configuration is anti-parallel, this electron, when it comes into the height electrodes, is in the minority spin direction because this magnetization has been reversed, and there is no states to accommodate it, and the current cannot go through the channel. And so the resistivity is much higher. This to say that, in fact, the advance came not only from the progress in the technology of the fabrication of this tunnel junction, but also to a relatively subtle understanding of the wave function in this material and on the connection between the wave function at the interface between the electrode and the tunnel barrier. And okay, so now these MGO tunnel junctions are the base of most of the application. And this also other challenge, finding also what was the best will be finding what is called an half metallic material. That is a material which is metallic for one of the spin direction and insulating for the other, so that there will be 100% of polarization. So the theory has predicted this type of property in some oxide, in manganese, in other alloys. So this is an example of tunnel junction with a manganite electrode separated by an insulating barrier. For the moment, there are some very good results, for example, for this type of barrier, that we have obtained 20,000 persons, so a large, an increase by a factor of 20 between parallel and anti-parallel, but only at low temperature. So finally, the same difficulty in obtaining a good result at room temperature in this new magnetic material is one of the difficulties. And this direction of research has been relatively disappointing. But what we have learned is to some expertise in the growth of this tunnel junction, in the control of the quality of the interface, and this is useful in other fields. For example, recently, a very interesting direction of research came from the finding that at the interface between two insulating oxides, there is a two-dimensional electron gas, a conducting two-dimensional electron gas. And this is a new type of two-dimensional electron gas that can be very interesting in electronics and also in spintronics because it can be combined with many magnetic oxides. And for example, we have also extended our expertise to the fabrication of this tunnel junction, to the fabrication of tunnel junction with ferroelectrics instead of ferromagnetic. For example, BTO, this oxide, which is a well-known ferroelectric material. And what has been found that by really growing with a very carefully this layer, it was possible to obtain the ferroelectric property even for very small thickness 2 or 3 nanometers of these materials, and finally to fabricate tunnel junctions with ferroelectric barrier, for example, this tunnel junction. And by the good surprise was to see that what we call the electroresistance, the difference of the tunnel resistance depending on the orientation of the ferroelectric polarization was very different. The TER, tunneling electroresistance of 75,000. That means an increase by almost a factor of 1,000 between parallel and between the two orientation of the polarization of the ferroelectric barrier. This is because the ferroelectricity, depending on the orientation, changes the distribution of electrons at the interface, and the distribution of the interface is very important for the tuning. It determines the bonding of the electrons wave function in the electrodes and in the material. So this, and we have also obtained tunnel junction with very high electroresistance. This can be interesting for the FRAM memory. FRAM are memory-based storing the information in the ferroelectric polarization of a ferroelectric material. And at the moment, this FRAM exists, but the detection, the reading, is obtained by a capacitance effect. And this is not a very convenient process because this is a destructive reading. And this experiment opened the way to a new type of FRAM memory with a reading by the tunneling magnetoresistance. One can read the orientation of this layer of BTO by looking simply at the resistivity and to the strong difference between the two orientations of the ferroelectric layer. So this, okay, we started with Spintronics and we are now in ferroelectricity. This is the life of the physicist in general. So I proceed to one of the most active directions of research in Spintronics today, spin transfer, manipulation of magnet by spin transfusion from an electrical current. The concept is very beautiful, has been introduced by John Solonensky and also by Luc Berger in the US. Suppose that with a first magnetic layer, you have prepared a spin polarized current. And suppose that the spin polarization of the current is obliquely oriented with respect to the magnetization of this second layer here. So this current will go through the second layer very rapidly. The strong exchange interaction with local spins will align the spin polarization of the currents in the direction of the magnetization. But the exchange interaction aligning this polarization is spin conserving. So from the conservation of the total spin of the system, what has been lost by the electron when they have crossed the layer has been given to the total spin of the layer. So that means a rotation of the spin, or in other words, a torque acting on the magnetization of the layer. And so this spin transfer torque can be used for different manipulation of the magnetization of layer or small objects. In general, because one needs a relatively large current density to move the magnetization, the massive magnetization of a magnetic layer, for example, the current has been confined in small section to obtain this high density. For example, in this structure, magnetic pillar tunnel junctions prepared by E-beam lithography. In general, you can see the size of the pillar of the order of 100 nanometers, or simply also by injecting through a small nanocontacts into a tri-layer to confine the current in a small area. And I will describe the two regimes, switching of the magnetization by spin transfer at low field, or generation of microwaves at larger field in general. So this is these two regimes. At low field, you can, by using the spin transfer torque, simply reverse the magnetization in this way, from parallel to anti-parallel. But if you apply a field, you can destabilize completely, you can prevent the complete reversing of the magnetization becomes too hard, and the system is set in a state of steady precessions with emission of microwaves. So I begin with an example of the switching regime. The switching trajectory is not as simple as you can see on this figure. In fact, the spin transfer torque acts as a negative friction, is equivalent to a negative friction, so it can enhance a small fluctuation of the magnetization progressively to finally switch the magnetization on the other side. And the reversal of the magnetization is detected by the GMR effect, by looking to the increase of the resistivity between parallel and anti-parallel. You can see on this figure, for example, as a function of the current, the increase of the resistance, revealing the switching from parallel to anti-parallel. And by reversing the current, you can now switch the system from anti-parallel to parallel. So the current density are relatively high, but what is interesting for application, that the switching time can be very short, 1/10 of nanosecond, and this is very interesting, for example, for the switching of the new generation of MRAMs. This is another example of reduction of the current density. Now the electrodes are not permalloy, like in this sample, but gallium arsenide doped with only a few % of manganese. So the number of spin to reverse is small compared to permalloy, and so one needs a smaller current. So the curve is more or less the same, but you can see the scale. Now the current density required to reverse the magnetization has been reduced by 2 orders of magnitude. So there is certainly several ways to obtain reversal at realistic current density. Application of this switching by spin transfer. In fact, the new generation of MRAM, STT RAM, will use, instead of in the first generation, on the market already, the switching of the magnetization of one of the electrodes of the magnetic tunnel junction, the memory cells here, was obtained by current pulse, and in these lines, generating magnetic fields, so that the combination of the two magnetic fields were able to switch the magnetization of one of the electrodes. But this is not a very local addressing of the memory cells. There are risks of crosstalk, there's a limitation to the distance between the cells, and so this is one of the limitations of the first generation of MRAMs. The new generation developed in many companies today will use the switching of the magnetization of one of the electrodes of the tunnel junction by spin transfer. And there are already very concrete projects of integration of this STT RAM on the processor of tomorrow. For example, the most frequent application that is described in several papers in this one, replacement in the processor of the CMOS memory, which is at the side of the CMOS logic in the processor, by STT RAM just embedded just on the top of the logic part of the system. And it seems that this not only reduces the size, the better integration of the component, but also reduce the number, significantly the number of transistors, so reduce the energy consumption, and certainly this sort of application can have a significant impact on the technology of computer. Actually, this type of I would call hybrid component, combining conventional electronics and spintronics, I guess, the first example of this hybrid structure combining semiconductor and spintronics. For example, there are several concepts that have been proposed of spin field effect transistor or universal logic gate, combining semiconductor channel and several electrodes, magnetic electrodes. I would say that, in fact, one of the problems today in electronics is what will be beyond CMOS. And okay, this is not exactly beyond CMOS, but this is a type of component that can push a little more the evolution of Moore's law, a little more before maybe a more revolutionary evolution beyond CMOS. But in fact, the SCT-RAM are already an example of something pushing a little more the integration of the electronic components. The second regime of spin transfer, when applied field is when you apply a field on the system, it becomes harder to reverse completely the magnetization. And so the only solution for the magnetization is to precess. You can see example of the trajectory of this precession. And during this precession, there is, of course, a periodic variation of the angle between the magnetization of the polarizer, this layer preparing the spin polarized current, and the magnetization of the free layer, what we call free layer. And so due to the GMR effect, there is a periodic variation of the resistance of the tri-layer. And so there is a periodic variation of the voltage between the top and the bottom of this structure. And if one looks with a spectrum analyzer to the voltage between the top and the bottom, one sees an EC signal, one sees a microwave power with this line, this spectrum of microwave power with so generation of microwave oscillation in the range of the gigahertz. The interest is that several interesting applications to telecommunication can be considered. The advantage of what is called STO, spin transfer oscillator, there are several important advantages. The main is the agility, the possibility of controlling the frequency simply by tuning the electrical currents, which can be done very rapidly and very easily. And so this advantage is important for many applications, for civil and defense application, of course. And there are other interests of this very small device, some micronic device, for on-chip integration. For example, there is some project of read heads of hard disk where a STO is integrated in the head to help write the information with a magnetic field. But a microwave field can help this writing process, and some projects of hard disk are using STOs to produce very locally the microwave excitations. There are, in fact, to proceed really to practical applications, there are several challenges. It will be necessary to increase the power, and we'll see how it can be increased by, for example, by going to the excitation of vortices or by synchronization of a large number of STO to multiply the power by the square of n. It will be necessary also to go to some spectral purity, to reduce the line width of the emission below 1 megahertz. Oscillation without uplifting will be necessary also for practical device, but this is relatively easy to obtain. For example, one of the ways that I want to discuss is, in fact, by introducing very different spin relaxation time in the two magnetic layers, is possible, if one look at the transport equation, to distort completely the distribution of spin accumulation, what is called spin accumulation in the structure. And so then finally to distort completely the angular dependence on the torque, and finally to obtain very different behavior than the standard behaviors that I described, and finally oscillation at zero field. I don't want to discuss the point. I want to discuss how to increase the power of these STOs, of this spin transfer oscillator. First, to proceed from metallic structure to tunnel junction. especially tunnel junction with the MgO barrier, which have a very large magnetoresistance. Of course, with the large resistance of the tunnel junction and also the large magnetoresistance, the variation of resistance as a function of the angle, the periodic variation, become very large, the voltage become very large, and the power can be increased significantly. For metallic tri-layer, the power is in the picowatt range, and for tunnel junction, we have obtained microwave power up to 2 microwatt, which is close to what is needed for applications. The disadvantage of this tunnel junction is still that the width of the emission is too large. 62 megahertz and 1 megahertz will be ideal. But in fact, there is other ways to produce microwave oscillation, not with precession, but with the rotation of magnetic vortices. Fact that we obtain in this type of tunnel junction, where now this free layer is thick enough to stabilize a vortex configuration. This is a vortex configuration of the magnetization, where there is no pole, no magnetic charge at the surface. It can be destabilized for some thickness. You can see sample image revealing from the succession of black, gray, and white, this rotation of the magnetization around the dot. And what can be done by spin transfer is sort of rotation of the core of these vortices in this way, like that. In fact, the spin transfer torque will produce these rotations here, so that when the vortex is on the left, for example, this means that in the major part of the dot, the magnetization is in this direction, but when the vortex is on the right, the magnetization in the opposite direction, in the major part of the dot. That means that in the major part of the dot, there is a periodic variation of the magnetization, and of course, this also produces a GMR effect or a TMR effect and an alternative signal. You can see some spectra of microwave power produced by this emission, around 1 gigahertz, but now with a very, very thin lines which are very appropriate for application. So the progress has been significant in this field. For the moment, the power is still too small, but this is because it's not the ideal. In fact, in this structure, one needs an out-of-plane polarization of the currents, but when by applying an out-of-plane field, but when the magnetization becomes completely out of plane, then the angle between the magnetization in the free layer and the magnetization in the polarizer is always 90 degrees, and so the magnetoresistance can be very high. So there are several tricks to overcome this difficulty and certainly to obtain large power and at the same time a good spectral purity. In addition, these vortices can be synchronized relatively easily. In fact, we obtain this vortice also in nanocontacts by injecting a current into a tri-layer through a nanocontacts. In this case, the vortex is stabilized by the Hirschsprung field, the circular Hirschsprung field generated by the current in the nanocontacts, because now this is a low energy if you put the configuration in a vortex configuration. And I can say a few words on nanotechnology. We can obtain very small nanocontacts by nano-indentation with a STM of a layer of resist on the multi-layer this way, and then by filling the depth of the penetration is controlled by a resistive control to go just at the top of the multi-layer, and then one fills with a magnetic material to obtain this sort of structure. So this was simply a comment on the technology, that you can see that this type of technology allows to prepare nanocontacts of only 10, 20, or 30 nanometers. And suppose with only one nanocontact, again, it is possible to generate a rotation of the core of the vortex due to the spin transfer effects. And then when we put on the same sample an array, for example, 4 nanocontacts to induce 4 vortex, when the distance is only 2 microns, it's too long. There is no interaction enough between the vortices in different nanocontacts, and we see only 4 lines corresponding to the 4 nanocontacts. But by decreasing this distance to, say, half a micron, now there is a synchronization. That is, you can see this line progressively emerge into 2 lines, and finally in a single line with a larger power and a very narrow line this time. In fact, the decrease in the width is significant. The width becomes smaller than 1 megahertz, and there is also an increase, significant increase of the power by synchronization. Finally, you see, this is a domain in Spintronics that is improving, advancing rapidly. I suppose that in simply, say, 4 or 5 years, there will be a telecommunication device based on this type of oscillator. You will see that we see that we can do many things with the magnetization. And with this spin transfer effect, it's really possible to manipulate the magnetization of a magnet in very different way. I will mention another manipulation with possibly can have also interesting application. So this is a nanowire, magnetic nanowire with magnetization pointing to the left and to the right in the red and blue parts of the sample. In between, there is what is called a domain wall. And one of the effects of spin transfer is the possibility also to pushing and to moving the domain wall by sending an electrical current. So it's motion of a domain wall by an electrical current. An experimental example, this is a nanowire. You see the scale 5 micron, and the image, I don't explain the techniques, the domain wall is the frontier between dark and white. And you can see by sending small pulse of current of 5 nanoseconds, it's possible to move progressively the wall from this position to this one and to this one. So this is an interesting effect to move the magnetization. And one of the applications which is well-known now, which is a project of application, is a project launched by IBM, by Stuart Parking of IBM, of a new system that could replace the hard disk. The hard disk is very interesting, it's very cheap memory, very massive, but the disadvantage is that there is a mechanical part, and so it's not very robust. If your computer falls on the ground, you can break the mechanical system of the hard disk. And so the idea is to have the same massive memory, but only with a solid-state device. And so the principle is to store the information by domain walls. Domain wall can be trapped at some notches, and if there is in this nanowire a domain wall, this will be 1. If there is nothing, there will be 0. So you can store the information in this train of nanowire. And the idea is then to prepare, to deposit in some trench of silicon, this sort of ribbons of nanowire, this way, and then with an electrical current to move this trend this way, so either to write some new domain wall at this point by an electric magnetic field, or to read the information with a GMR sensor. And so this project, the project is to obtain the same capacity as the hard disk, but only with a solid-state device and the robustness of solid-state device. Okay, so I will end now, I suppose maybe 2 or 3 minutes, with a few words on other fields in spintronics today. Spintronics with semiconductor, spintronics with molecules. Spintronics with semiconductor, of course, is very attractive to combine the potential of conventional electronics, that is the coupling with optics, the possibility of current modulation by electrical voltage with a gate, and the potential of spintronics, not only the non-volatility, but also many other possibility of current modulation by acting on the spin. And there are several concepts of spin transistor with the concept of gates. So the research is following two ways mainly: combining magnetic metal, usual magnetic metal, with semiconductor in hybrid structure. This work, for example, this is an example of spin LED, light-emitting diode. One inject from a ferromagnetic metal through a tunnel barrier, a spin-polarized current into a LED, and the spin polarization makes that the emission, there is emission of circularly polarized light. So this is to emit directly a circularly polarized light with a spin LED. The other way is to prepare magnetic semiconductor based on the conventional, on the usual semiconductor like gallium arsenide. So, for example, this one, a good gallium arsenide doped with manganese, has revealed many interesting properties. I have showed some results of spin transfer, of switching or magnetization with a tunnel junction. They show a large TMR results, but the current temperature, the temperature below which the material is ferromagnetic is only 170 Kelvin. So for the moment, this sort of compound cannot be used for application. Room temperature is needed for most application. And so the challenge is finding also other ferromagnetic semiconductor working at room temperature. Several announcements have been made. I would say that the situation is rather confused on this front, actually. At the moment, there is no ferromagnetic semiconductor really working at room temperature. So the best way for the moment is this one, the combination of ferromagnetic metal and semiconductor, and several devices have been proposed based on this combination. Well, I can say that the STT-RAM already a sort of combination of magnetic metal and semiconductor, but more integrated components have been proposed, like logic gate or a spin field effect transistor based on this structure, a semiconductor channel between a ferromagnetic source and a ferromagnetic drain. Some concept also of logic gate. The progress has been relatively low. In fact, there are several difficulties in this on this way. In fact, in this sort of structure, what one needs is that the spin of the electron is conserved, does not flip during its stay in the channel. One needs that the dwell time of the electron must be longer than the spin lifetime, and this is relatively difficult to obtain with semiconductors. The velocity of the electron is small. Generally, there is a strong interface resistance, so the electron is not transmitted directly. There are several rebounds. The dwell time is generally too long to obtain good property of this type of device. On the contrary, in my opinion, much more promising materials are carbon-based materials. In fact, nanotubes, graphene, and several types of molecules. Why? First, due to the small spin-orbit coupling of carbon, the spin lifetime is known to be too long and is expected to be sometimes very long. So, and secondly, also, the velocity is very high. This is interesting for the dwell time. The electron can propagate from, for example, source and drain very rapidly. And this velocity, due to the unique dispersion relation, linear dispersion of these materials, like graphene or carbon nanotube, this velocity is high even for small carrier concentration. So there is, these materials are very promising for the most of the spintronic application. I'll show you an example of experimental results that show the promising property of carbon nanotubes. Works that, in fact, had been done in this paper has been published in collaboration with Louis Fresseau, which is not a nanoGUNE in San Sebastian. So experiments of spin transport on a carbon nanotube. This is an artistic view between two magnetic electrodes. This is a picture by electron microscopy. This is a nanotube between the two electrodes. This is like a GMR structure. This is in GMR, you can have iron and cadmium and chromium in between. This is a nanotube. But we have seen that in GMR, the distance between the two magnetic layers must be of the order of a few nanometers. And you can see that in this experiment, instead of a few nanometers, the length of the carbon nanotube can be more than 1 micron, and the GMR effect, the difference between the resistance of the anti-parallel and parallel configuration can be very large, 60%, 62%, even if the distance is 1 micron, 2 microns. So this means that the spin can propagate to very large distance in this type of carbon-based material due to the small spin-orbit coupling and to the large velocity of the electrons. Okay. For example, in the experiments, the spin lifetime is long, 50 nanoseconds, and finally, the spin propagation in the nanotube can be to about 30 or 40 microns. And so it's interesting to have materials like carbon nanotube or graphene in which a spin can be propagate to this long distance. There is a space, there is a possible space for several logic gates, for example, on this distance. And there are several concepts that can be imagined by using this spin propagation to long distance in this material. I will say a few words on the concept of spin current, pure spin current. What is a pure spin current? Suppose you have a non-magnetic channel and you inject spin polarized electron here. The current is going this way to the left. So there is, because the current is larger for the spin-up direction in the ferromagnetic material, there is, at this point, accumulation of the spin-up electron and depletion of the spin-down. This can be represented by the splitting between the Fermi energy, between the chemical potential of spin-up and spin-down. And so finally, if you have this accumulation, this larger Fermi energy for this spin direction, smaller for this one, that means that this spin-up electron will diffuse to the right, and on the contrary, the spin-down will be attracted to the left by this depletion of the chemical potential. And finally, there will be in this part of the sample what is called a pure spin current, so equal currents in opposite direction of spin up and spin down. This is a pure spin current, which is interesting for several effects. With only no charge current and only spin current, there is no capacitance effects, which is can slow down the response of many electronic components. There are other advantages I have no time to discuss. And finally, also, one can speculate that there are some possibility of completely new concept, for example, of logic based not on charge current but on spin current. In the conventional logic, one is large voltage or zero voltage. You can store the information only by the direction of the spin polarization, this direction of the perpendicular direction. So it's possible to conceive other type of logic gate based not on the propagation of charge current, but the propagation of spin currents. And finally, one can speculate the possibility of having a new type of electronics for computing with some processing units with only spin currents, of course, between some classical CMOS input and output. So there is one of the concepts that are now considered in Spintronics in this direction. Okay, so I have still two other slides I will skip. So we have seen that Spintronics is developing in many directions. This is a roadmap from Japan on Spintronics. There are many other directions that I have not described, for example, quantum information, quantum computing with Spintronics, spin photonics. I say a few words on storage, on MRAMs. So I don't want to discuss all the other directions of Spintronics today. The only thing, my conclusions will be only that Spintronics is a relatively new science, 20 years, more or less, but this small baby is growing very well. What I illustrate by the last transparency, Spintronics electronics, we don't know if the small baby will also grow at the same size as the electronics mom.
How reproducible was the synchronization of the 4 vortices? In other words, how many devices have you measured, and how many of them have you seen the synchronization?
We have not measured many devices. We worked, say, 4 times. We are just at the beginning of this study. In fact, we have another way to synchronize. We also synchronize by electrical current. It works also relatively easily for vortices by synchronizing by electrical connection, so that each STO generates an EC current that acts on the others. And so it seems that also by this way, it's relatively easy to synchronize the vortices. This is more recent. Maybe I suppose you are at ICM, no? Yes. No?
Okay, so thank you very much.
Thank you. Okay, thanks.